This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. Okay, so now we get on to defining closed sets. So we say that y in x in Rd is closed in x if the complement x less y is open in x, right? And for now, we can just define things as closed in x or open in x, because you can just replace x with Rd and then recover those definitions for the more general case. So here's a few examples to kind of get us used to the idea. The open interval 0 to 1 is open in R. So that means that its complement, minus infinity to 0, closed, union with 1 to infinity, closed here, is closed in R. Here, this sort of lower half of the real line is open in R, so this upper half is closed in R. This set here, open bracket 0, 1, close bracket, is not open in R. Its complement has this form here, but it's also not open because we wouldn't have wiggle room around this point here, 0. So that means that this interval here is not open or closed. So open is not the opposite of closed. Things can be both open and closed, can be neither open and closed. So don't just look at a set, see that it's not open, therefore must be closed. I say that all of these intervals of this form are closed, and that should be easy enough to check. R less those intervals is just the union of two open intervals, so therefore it's open. This individual point here, 4, I say is closed because the complement is just the union of two open intervals, which is again open. Here, if you did the exercise from the last video, you'll be able to check easily that all of these closed balls are closed in X, because I asked you to look at the complement of this, where the inequality is flipped and becomes strict. That's when that would be the complement of this set, and that would be open. And for example, this, you can check this set as well as closed. So it's just all the points in R2 where y is 0, so just a line. And the complement of this would be the upper half plane and the lower half plane, the union of those two. And that's of course the union of two open sets, so it's open. Now we can use all of our topology rules for open sets with closed sets as well. So we're just taking complements. The complement of x is the null set. So if x is open, then the null set is closed. And of course we had that the null set was also open and its complement is x. That's also closed. So the null set and x are both closed in x for any given x in Rd. Finite unions of closed sets in X are closed in X, and arbitrary intersections of closed sets in X are closed in X. And these are just the converse, or the complement statements of the ones that we had for open sets. So from this statement number 2 here, and using the idea behind this exercise here, where just a singular point is closed, in Rd, all individual points are closed. So therefore, if x in Rd can be expressed with finitely many elements, therefore it can be expressed as the finite union of all those individual points. So therefore, it's closed. So sets with finite elements are closed. Now we can look at convergence in terms of closed sets. So if we have y in x in Rd and y is closed in x, and we have some sequence of points in this closed set y, and it converges to some p, not necessarily in y, it can be in x, well then we're claiming that actually it does necessarily have to be in y, that p lies in y. And here's some pictures to maybe show you why that wouldn't hold for open sets, and an example. So you can look at this with the boundary, this dashed line of this open set, and our sequence can approach it, but because that point doesn't actually line the open set, we can get arbitrarily close to it and never actually reach it. But in the closed sets, we use a thick line to denote the boundary is included, and the sequence would have to converge. The sequence is allowed to take values on the boundaries, therefore P must be within this closed set too. So returning to this example where xn is just 1 over n, we know that this sequence converges to 0. But for any given value of n, xn, 1 over n, is just in between 0 and infinity, but with a strict inequality here. It never, for any value of n, it never actually takes the value of 0. But the limit, as I said, of the sequence is 0, which does not lie in this interval. So that's an example, because it's an open interval, so this statement fails to hold then. So we can move on now to the idea of interior enclosure. So they're sort of what you would expect them to be. We just have to mathematically define them now, and we do it with the open sets and closed sets. So for any set in RD, the interior of that set, which we denote by X with the little circle, it's the union of all the open sets that are in X, or if like it's the largest open set contained within X. And the closure of X, which is X with a bar on top, is the intersection of all closed sets containing X. So it's the smallest closed set containing X. So the idea behind the interior is to basically make X, you remove as little as possible until X becomes open. And for closure, you add as little as possible to make X closed. So I've done that here with this interval here, which you've seen is neither open nor closed. Its interior now becomes open because it's going to be the biggest open set within this, which is clearly this, because we just got rid of the endpoint. And then the closure would be this closed interval, because it's going to be the smallest closed set, which contains this, but you have to add in one extra point. The idea for the open ball, the closure of the open ball just becomes a closed ball. We just have to change this strict inequality to a non-strict inequality. So essentially, if you have the open ball, you're just adding in the boundary. So you're adding in all the points on the outside. For a singular point, its interior is the null set. You can't, if you only have one point to remove, then, or even if it was violently many points, its interior would still be the closed set, because you have to remove all of them to get the empty set to make it open. But its closure would just be itself. So you can, if you take the closure of a closed set, it stays closed, and the interior of an open set stays open. And then just the boundary, I've been saying this for a while, we can formally define the boundary with this symbol here, del x equals the closure less the interior. So it's just, as you'd imagine, the boundary. So here, the boundary of this set here will be the closure less the interior. But it's just the points 0 and 1. And here the boundary would just be just the sphere, not the ball. So that this would change to an equality. Some properties of interiors and closures. For any set, the interior is always contained within the set itself, which is always contained within the closure. If we have y inside of x, then the interiors and the closures will also be inside in that same order. Now, x is open if and only if it is equal to its interior. It's closed if and only if it's equal to its closure, which sort of makes sense. The smallest closed set containing set that's already closed is the set itself, and the largest open set contained within the set itself, if it's open, should be the same set. We can now define neighborhoods. So for any given point x, if it's contained within an open set U, we just call U a neighborhood of that point x, and we'll denote it by just NBD for short. So we can use this to check if a point x lies within the interior or the closure. So x lies within the interior if and only if some neighborhood of x is contained within the larger set. So here we can see that X lies within the interior, and that means we can just take some open set U which contains X. It doesn't have to be a circle or a ball surrounding X. It could be some abstract shape as long as it contains X and it itself U is entirely contained within this set X. And I've drawn X this way because it's kind of neither open nor closed, so it would have a good notion of interior and closure. So the idea is that maybe we'll have to like stretch and morph this U to make it smaller or squeeze it so it can fit entirely within X. As long as it's contained within the set and contains the point, we're all good. X will lie within the interior. Now, if X wants to lie in the closure, we need that every neighborhood of X has to intersect the set. So if X lies within the interior, then it definitely lies within the closure because of this property here. But what if X was lying on the boundary? So it was just lying on the closure without lying on the interior. Like this point here, Y is. Well, we can see that no matter how we squeeze and stretch this neighborhood of Y, V, it'll always intersect along here with X. Because it's an open set. So open sets need to have wiggle room around all points that they contain. So if we were to wiggle around this point here, Y, we'd always have to be able to wiggle a little bit to the left. So we'd always have to intersect a little bit with X. So no neighborhood of Y could ever not intersect X. So that means that Y is in the closure. So we can now just briefly define limit points. So for any set X, if we take a point P, we'll call P, which is not necessarily in X, a limit point of X if every neighborhood of P intersects X at some point other than P. So a really clear example of this is if we take these two intervals, both from 0 to 1, we can see that 0 is clearly a limit point of both of them because any little, wiggle room left or right, in this case, of the point 0 will always intersect these intervals at, an infinite number of real numbers. Even though 0 doesn't happen to belong to this interval, it is still one of its limit points. The interesting thing about limit points is that if we have a set X, which has a limit point P, then we can always create a sequence in X which converges to that limit point P. That's why they're called limit points, because they have the limit of some sequence. And we just have this nice property here where the closure is exactly X union with all of its limit points, which makes sense. You can sort of see that in action here. The closure of this is this. So it's just going to be the limit points of this, which has 2, 0, and 1. Just add those in.